analysis and risk interpretation. And so what this means then is that we're leaving stakeholders to make sense of what climate change will mean for themselves. And that means potentially muddling through an ocean of climate data and sometimes conflicting recommendations on what data should be emphasized when you're thinking about planning exercises. So again, that brings us to today's topic. I'm just going to quickly bring up a slide here. I'm not going to spend a lot of time speaking to it, but maybe it just sets the stage a little bit. This is how I end up thinking about these things all the time. Climate change scenarios are potential socioeconomic futures that we plot out and feed into climate models to give us a sense of how the Earth system might respond and what kinds of climate conditions we'll be looking at in the future. And this then is what's being used to feed or being used as guidance ultimately for planning actions at the moment. So recognizing that this is the tool that we have available, we might ask ourselves a couple of questions about which ones we should use. And we are seeing, again, some conflicting opinions on this these days, with some arguing that some of the higher impact scenarios, things often referred to as business as usual or fossil fueled futures, are too extreme to warrant serious consideration and planning, while others are arguing that ignoring these high-end scenarios means discounting very real climate risks. Now, until recently, these disagreements felt like they were largely contained within academic and specialist circles. However, as more stakeholders turn to climate projections for guidance and governments are setting more and more climate policies, it is gradually starting to leak into other arenas and could have potentially serious consequences for our climate preparedness and risk awareness. Now, we're lucky today to have a range of experts available to help us make sense of these climate scenarios and their use and some of these conflicts. From the University of Waterloo, we have Dr. Vanessa Schweizer, whose wide-ranging expertise includes physics, philosophy, communication, engineering, and public policy. Now, most importantly, Dr. Schweizer is an expert on scenarios and their use in decision-making and sits on the International Committee on New Integrated Climate Change Assessment Scenarios, also known as ICONICS. From Queen's University, we have Dr. Christian Seiler, climate scientist whose research helps us understand how climate change will ultimately impact the land surface, vegetation, and certain extreme events. And in today's webinar is here to help us understand how Earth system models translate some of these socioeconomic scenarios, or SSPs, or climate change scenarios into possible climate impacts. From Memorial University of Newfoundland and Labrador, we have Dr. Joe Daraio, who's housed within a civil engineering faculty, but also has expertise in geography, ecology, philosophy, and climate adaptation. And this includes making sense of climate data for the purposes of engineering design, so putting model output into practical application. And finally, we have Dr. Sabine Dietz, Executive Director of CLIMAtlantic, a climate services organization serving all of Atlantic Canada. And Dr. Dietz is deep in the climate planning trenches at the moment, helping all of the Atlantic provinces to access, interpret, and apply climate data, and is seeing how some of these discussions are playing out in real-world decision-making. So I think we're going to start with just some quick introductory words from all of our presenters. We'll start with discussion of scenarios and how they work with Dr. Schweizer. Thanks, Dr. Schweizer.
Yeah, thank you very much. And I want to thank everyone again for participating today and for even having this webinar, because I think it's very important. I will also grab my slides really quick to make a couple of contextualizing remarks with respect to scenario analysis and how it is implemented in climate change research. So give me just a moment to switch over to that. And I think, oh, here we go, share. And let's say present again. Okay, so hopefully I think you're seeing the actual presentation, which is good. So this is, oh, and I see that one of my animations is a little silly, but first we'll just look at like the figure shown here, which is very similar to the figure that Joel showed in his opening remarks, where he was saying that there are these different kinds of scenarios that have these labels, where on the left-hand side, you see that there are these different scenarios that are labeled as SSP1-2.6, SSP2, 4.5, and so on and so forth. And they're being fed out of these integrated assessment models to come up with some sort of GHG emissions projection. And then there's like further modeling that's done onto it to ultimately get some outputs from global climate models that you all as impact experts should be able to use. That's sort of the idea. So it's very key to appreciate that these scenarios that are generated by the climate change research community are an interdisciplinary product. And let me make sure, there we go. I've got like a little animation there where I like hand drew in that when I've worked with my colleagues in integrated assessment modeling, my understanding of where they even come up with these sorts of assignments to generate scenarios like SSP1 2.6 or SSP2 4.5, they actually arrive at these scenarios in conversation with physical climate modelers regarding what kinds of scenarios would be useful for these model intercomparison projects. So that's an important thing to understand, that from the very beginning, there's some collaborative discussion about the nature of what kinds of different emissions projections would be useful to the climate science community to actually run through their projections. So then in turn, that's where you get these different spaghetti graphs of what the different carbon dioxide emissions might look like. But it's important to appreciate that for the integrated assessment models, there are all kinds of very rich assumptions or specifications that they have to make in order to even come up with these emissions projections. And something that was an important finding from, if we go into like the history of climate change research and look at the roles that these scenarios have played in IPCC reports, it was around the time of the third assessment report that the integrated assessment modeling community found that you couldn't necessarily say, oh, if we just cleaned up our energy production systems, or if we just had really efficient energy use, this would automatically lead to lower emissions outcomes. It's actually a combination of things that influence what our emissions profiles look like. And so that's why behind the SSPs, and there was a launch that actually just happened this morning where I was attending a webinar by colleagues and collaborators that are at IASA, or the International Institute for Applied Systems Analysis. They have just unveiled a database that helps to convey how rich these socioeconomic scenarios are, because you can actually look up things like further projections that other social scientists, people who focus on like economics and whatnot, and also economic development, you can actually like dive into this scenario data and see how people have drawn conclusions about how, according to the different SSPs, you have like different shares of economic activity happening in agricultural sectors or in industry sectors in different countries of the world. So the point of my slides is to convey that these scenarios are very rich, and they are also interdisciplinary products. So part of what makes things challenging for you all, I imagine, in light of what Joel was saying, what does this mean that I'm hearing that these fossil fueled futures or business as usual futures are, and I guess I'll go back to one of those examples, like the SSP 585 projection, for instance. What does that mean if I'm hearing that this is not plausible? From a socioeconomic perspective, perhaps it's less plausible, because we do see that countries are announcing things like net zero targets. But then again, we're in 2024, we have yet to actually see these things manifest. So it is still very much an open question, right? What does it mean to say that just because national governments are making these declarations, does that really mean that that SSP 585 trajectory is actually implausible? And I imagine we'll talk about that more through this webinar. So I think I'll go ahead and stop my comments there and pass things on to another panelist.
Perfect. Next up, we have Christian Seiler to talk to us a little bit more about how these things then are fed into climate models, to give us a little bit more information of what those impacts will look like. Thanks, Christian.
Thank you, Joel, and thank you, Vanessa, for this wonderful introduction. And hello, everybody. I'm very pleased to meet here. It's great that there are so many people who are interested in the subject. I want to make 2 points in my brief introduction. I want to go back to Vanessa's very first slide. If you kind of screened it, you saw the same information that you see here. You have your socioeconomic storylines. You have your integrated assessment models that translate your storylines into greenhouse gas and also aerosol emissions. And then there is something that she called magic. That is a simple climate model with a coupled carbon cycle model that translates these emissions into atmospheric concentrations. And that part is important because about 50% of the carbon that we emit into the atmosphere gets absorbed by the ocean and by the biosphere. And of course, this carbon uptake depends on atmospheric CO2 concentration, and it also depends on temperature. So you need a simple climate model to convert these emissions into concentrations. And once you know those concentrations, you can then feed them into these full-blown climate models or Earth system models that eventually will give you your climate change projections that you can then use to have your climate change impact assessment. So there's this simple climate model that Vanessa called magic here that's really important to make this translation from emissions into concentrations. And it emphasizes the crucial role of the natural carbon cycle that has such a big impact on our fate. And that's where my personal research focuses on. How does the carbon cycle respond to changes in climate as well as CO2? And there are very large uncertainties around that. And that has such a big impact because if we wouldn't have this uptake of carbon from the ocean and the land, then the CO2 concentration in the atmosphere would be twice as high, and also the warming rate will be twice as high. Okay, but today's panel is about the scenarios that are produced by the Earth system models and about the question, are there scenarios that you can rule out? In my own research, I have always relied on these fossil fuel intensive scenarios because the carbon cycle is a very messy issue. There's a lot of noise associated with it. So to get a good signal to noise ratio, you want to have a very strong perturbation to provide qualitative answers to what is the impact of rising temperatures, what is the impact of changes in precipitation to the carbon cycle. So I always tend towards these fossil fuel intensive scenarios because they prove to be very useful for investigating the qualitative change that is happening in the Earth system. Concerning the question if there's something that we could rule out, personally, I think one of the scenarios that we can rule out with quite some confidence are these a very optimistic scenario. So SSP1, for instance. For SSP1, you really need to be reducing your emissions already to the extent that you actually have negative emissions. So you take out more CO2 from the atmosphere than you emit. And well, that would be consistent with the 2015 Paris Agreement, but the problem is that there's a huge disconnect between the Paris Agreement and the actual emissions. So this is shown by the emission gap report or production gap report that you see here on the left-hand side. On the horizontal axis, you see the time. On the vertical axis, you see the amount of CO2 equivalent emitted per year. And the blue shaded line gives you the emissions that you would want to have in order to be consistent with the 2015 Paris Agreement that wants to limit global warming by 2 degrees or far below 2 degrees, preferably 1.5 degrees. But you see the red line is the line that is actually happening right now. So the government plans and projections. So right now, I don't see how we can get on a pathway that is consistent with SSP1. So if there's a scenario that I would rule out, it would be that one. Thank you very much. And with that, I'll be happy to give over to the next speaker.
Perfect. Thanks, Christian. So next we have Dr. Joe Daraio, who's going to take us more towards away from the thinking about this in theory and what this does potentially to our climate system into how we work with those outcomes, specifically from an engineering perspective. Thanks, Joe.
Lost my mute button there for a second. So I'm going to go over an example. So I need to put this in context in order so that you can better understand. So there's a method called the observational method that's been employed, and it's from geotechnical engineering, and it's been around since the 50s. And it provides it's actually a really good framework and it's relatively easy to use this in a climate change context. So I know there's a lot of words here. So this is my beginning and end are wordy slides. So this observational method, it continues to manage integrated process of design, control monitoring, and these are design modifications that can be incorporated during or after construction as appropriate. So the ultimate goal is have safety, or I should say, be efficient, greater economy without compromising safety. Safety, of course, is key. So this is a really good kind of way to think about climate change, and it's been implemented. I'm going to give you a couple of examples. So there was a high-speed rail line between Miami and Homestead, Florida. And this was going to be along the coast in a lot of areas. So they had to design this with sea level rise in mind. And the graph on the right here, I know there's a lot there, but these are the 95% and really the 99 percentile water levels based on the three different scenarios. I don't know which ones don't matter so much, but it's best case, kind of middle of the road, and then a worst case, right? And you can see how sea level is projected to rise. All right, so when engineers take this kind of approach, in general, especially using the observational method, your current design for a piece of infrastructure that, it depends a lot on the intended lifespan of this, but you need to make sure you're designing for the entire lifespan. So if you've got something that's designed for 50 years, you have to make sure you're designing for 50 years in the future. And obviously climate change is important there. So it's initially based, the initial design now is based on the most probable future climate conditions. And then you have to add course of actions for modifications for within this method, the terminology is unfavorable foreseeable deviation from these most common, most probable conditions. It's a bit ambiguous, and it kind of leads, it's kind of one of the things we're talking about, right? But the key is here, we're designing for, at present, for the most probable conditions. So let me, the next few graphs I'm going to show you. This, on the y-axis is the predicted sea level. That values don't matter so much. And of course, we got the year on the bottom. So when you're looking at these years, these are when decisions are made. So we make our initial decision based on our most likely, or most probable future condition. Can everybody see my mouse there moving around? Good. And so this is the initial design, but engineers are going to plan based on the worst case. They're going to say, okay, what kind of modifications do we need to make? And then the time comes along and you can make those modifications. And here you see that in this case, we've got decreasing uncertainty as we move through time. Aleatory uncertainty is just that uncertainty really due to natural processes. You can't really eliminate that. And then epistemic uncertainty deals with our knowledge, and our epistemic uncertainty is reduced under this scenario, and we can make the necessary adjustments as we go. This is a case where we're actually have a slightly decreasing sea level, which is not realistic, but it just illustrates that if we design for most probable future conditions, we don't need to make any changes. We might be a little over designed, but that's probably not a bad thing to have. And this one here is kind of maybe the more realistic type of thing we face now, where again, we're designing based on our projections today for the future. And then as we understand the climate and get more certain on what the projections are going to be, we can make those adjustments. However, a big part of this, in addition to the first two steps, is that you need monitoring, and that's really, really important. And that's always a big issue for these kind of things for engineering. And these potential modifications are under this method. They should be identified prior. So we should, again, this is what kind of modifications do we plan for, which is why we want to keep the worst case in mind, but hope for the best in a lot of ways. So here, yeah, so that's kind of the plan. This is a different, from a different project. This is in California, but it illustrates the process. So same type of thing. Sea level rise, you have the train along the coast. We know we're going to get increased sea level rise. You don't know how much. If you then look at the most probable, then they can make that design for now, and then allow for raising of the deck of the tracks in the future. The important part here is that the base of this needs to be designed to handle that extra height and extra weight. And these are the things that need to be done at the start of a project, which can be challenging due to the uncertainty, right? So when we think about the observational method, this is stated, it should not be used unless the engineer has pre-selected a course of action for every unfavorable situation that might be indicated by observations. So that shows its dated nature, really, because we know we're not in a stationary climate anymore. So this is not as valid. So there's, it can be adjusted. And I should say that the observational method, I present this as the first exposure to adaptation to my students in my climate change courses. In any case, when we use scenarios from the engineering context, as is illustrated in the examples, we're usually at least three, where we want to really bracket the potential impacts. Where again, the middle one, the most probable one, is of course one of those. Then we have a high, worst case, and perhaps the best case. And this is for maybe the most likely conditions is the initial design, and then the foreseeable, plausible worst case should be looked at as that's a place where we very well may need to go, even though we might not have to, but we need to be ready to go there, which means we'd have to use that worst case in order to do that. And so, even though it's maybe a very unlikely event or unlikely to happen, it's still plausible, though it's unlikely, and it still needs to be taken into account. So that's kind of the general way I think engineers approach, especially the large critical infrastructure projects in particular, where safety is paramount importance. So that's it for me. I'll pass it on to the next.
Perfect. Thanks, Joe. So now to Dr. Dietz. Let's talk about how things are looking inside of what I'm referring to as those climate change trenches these days when it comes to scenarios.
Yeah, thanks, Joel, for inviting me. Just up front, I'm a recent settler living in unceded Mi'kmaq territory. Just want to acknowledge that. So CLIMAtlantic is one of the number of climate services organizations across Canada who try to translate or be an intermediary between all of the stuff that was just said and the people that need to make decisions. And so that's it's a pretty challenging task, going back, for example, to a number of years where a counselor in my hometown said, oh, let's not use that worst case scenario because they don't know what they're doing. So uncertainty being translated in the scientists don't know what they're doing, to now where there's a lot of pressure on us as an organization to say, use this scenario or use that scenario. And our team having discussions around, we really need to change the conversation, because we're being asked to put a simple statement out there, while the story behind that simple statement is really complicated. So going back to what Dr. Seiler and Dr. Schweizer presented, all of those models are human created. They're not infallible. What you put in a model, if you put junk in, you get junk out. And I'm not saying scientists create junk, but literally the decisions made up front in all of those boxes that come after are really crucial. And so who puts what decisions in place, who makes what assumptions. So all the assumptions packaged into the model development and then into the scenarios that we're seeing. It's a complicated story. It's a complicated story when we're thinking about plausible, uncertainty, likelihood. So all of these are not stories that we can package into a simple statement. You should really use the worst case scenario, because what Dr. Daraio said is fairly straightforward in the infrastructure world. It really isn't in the public policy, in the political sphere. It isn't for private people. It isn't for municipalities, where essential decisions need to be made. So we're in a place, we're muddling right now. We're really muddling, trying to figure out how do we move people away from hey, I need to use one scenario, which should I use? Or I need to use two scenarios, which ones are the best ones? Or people saying, well, which scenario do I throw out and which should I keep? Where we're looking at more, well, what is your question? What are the things that you need answers to? And what are the decisions you need to make on the ground? And maybe it's not a question of scenarios, but maybe it's a question of, okay, if you really need to construct a major infrastructure piece, you want to maybe in Atlantic Canada at least look at Fiona, the Hurricane Fiona, and how it hit in various areas, incorporate that, instead of thinking, oh, I need to use scenario SSP, XYZ. So I think we're getting away from trying to, actually, our simple statement is we're not giving recommendations on scenarios. That's a line that our organization has taken. We're not giving recommendations. But we will point to Fiona. We will point to, so where are we on looking forward and the changes that are happening, and changes that we will see more and more happening around us. But our role is really to help people through that muddle. And it's not an easy muddle to get through, because the pressures are there to simplify. The pressures are there to really draw a simple line. And all of that, just to say that when you do this kind of stuff, you draw a simple line, you give a simple statement like use the scenario SSP XYZ, use that scenario for your planning, then you are assuming as an user, you're providing that kind of certainty, assumption of certainty that, oh, if I do this, it's okay. This is not the intended use of the scenarios. It definitely isn't, but it is the way they are being used. And there's a huge risk in that itself. So instead of the scenarios, let's talk about risk. Let's talk about what are you using this for? Why are you doing this? Is this the best way of looking at the future, the potential impacts that you'll see from climate hazards? So all of these questions, it's a way more complicated story than saying, hey, let's use SSP 5.8.5.
Excellent. Yeah, so I think that opens up some other points of discussion. That's a bunch of different perspectives on these things called scenarios. And Sabine, you've just referenced one of the key questions we get asked all the time, like what scenario should I use? What scenario should I use? And your recommendation now is, well, take a look at observations, but also take a look at, I'm not going to tell you which scenario to use. You should probably dig into most of them. I wonder if other panelists have responses to that particular question. What scenario should we use? How do we answer a question like that? Or how would you answer it from your particular perspectives? Are there right scenarios for right situations and wrong scenarios for wrong situations? I think we've heard a little bit from Joe and Sabine, but Vanessa, when that question comes up, what kind of responses feel appropriate to you?
Yeah, so something that feels very important to me to convey is that you want to look at more than one scenario for sure. And I also like the comments that Dr. Dietz was saying in terms of how she tries to engage the people that are asking her for advice to say, what are you trying to use these scenarios for? Because often it is through discussion that you get a better sense of sometimes a scenario is actually not appropriate, right? So maybe 0 scenarios is actually what they need, depending on what their question is. But if you do determine that you should be using scenarios, I would say use a minimum of 2. And if you can use more, that's even better to try to explore, what are the key differences in these outcomes of these scenarios that might impact the nature of the decision that you're trying to make.
Excellent. I think a quick follow-up question there too. I know Dr. Seiler was saying, I would that you would refer to the sustainable SSPs, the low impact, high action scenarios is how I tend to think of them, as the least plausible. Is there still a function for those optimistic but perhaps low plausibility scenarios?
Well, I mean, it's physically possible. Right now, we are emitting about 10 to 11 petagrams of carbon per year. Our carbon budget to be within the 1.5 temperature threshold is about 70 or by now 60 petagrams of carbon per year. So if we continue emitting as currently, we'll consume our carbon budget by 2030. So by then we will know whether you made it or not. Now, obviously, physically, it's possible to stop our emissions now or dramatically reduce them in the way that it's consistent with SSP1. But I just don't see any kind of indications that this is happening. I mean, it would be great and fantastic. It's physically possible. But at the moment of time, I don't see it being plausible. So there's no evidence for that. Which shouldn't take away the hope of this is not a yes and no situation. This is not a binary situation. Every fraction of a degree matters, of course, and we should start to reduce as strongly as possible. But I think it is important as a society to know that currently CO2 concentrations or emissions are not reducing. So last year was a year with the highest emissions ever. Concentrations are going up. So there's no reason to relax, basically.
So maybe those low-end scenarios are useful for communicating what we could potentially achieve if we set our minds to it, whereas those high-end scenarios are most appropriate for figuring out what risks we may be facing.
Yeah.
Is that a fair summary?
Yeah.
And maybe if I can just
Sabine.
throw in something, Joel, Dr. Seiler, there. The thing is too, you know, when you think about action, because this is all about making decisions about what do we do. And some actions that we may want to take under high-end scenarios are not the same as the ones under low-end scenarios. And so there's costs and all sorts of things associated with it. But in most cases, our decisions currently are really bad. They're just simply bad, even under a better scenario than, let's say, the worst case scenario, or a high emission scenario. And then I remember this cartoon in one of the newspapers where essentially the question is, well, you know, if 50 years down the road and we see, oh, we've managed climate change and hey, the impacts didn't happen and we did all these things, is it really that bad? Because I think, although what Dr. Daraio presented, that the idea that climate action is often associated with projects, so especially infrastructure projects, and there's a huge focus on infrastructure projects. But the fact is that adaptation isn't just that. And I would suggest strongly that it's actually the smallest part of that. Because if we manage to make our communities more resilient, which should be in climate adaptation our real purpose, then we address a lot of the other issues that we're currently facing, whether it's housing, poverty, unhousedness, whether it is, you know, mental health issues. If we adapt or make our communities more resilient, then we have a lot accomplished. And whether we really focused on aiming towards that high emission scenario and meeting the needs that requires, or the lower, the difference will be in how much better off we will be as communities. And so in that sense, that's where I think our focus on scenarios, and it's a strong one right now, and it's been sort of fiddling along, but it's getting stronger because the differences in what we need to pay is getting larger, and the investments are needed are getting so large, they're massive. But this concentration or focus on the scenarios creates a lot of danger in terms of that we forget what we actually need to do. And so just to go back to the way we see our role in CLIMAtlantic, we're less and less focused on projects, you know, what to do when. We will help, this is our role, but more and more on this adaptation thing isn't a project that we deal with. It's a long-term process, and we're in it for good in Atlantic Canada. Sea level rise isn't going to stop. Storm surges aren't going to stop. Extreme events aren't going to avoid us. Heavy rainfall events over snow. We just had flooding events again. They will not stop. So we got to deal with that from a receiving end perspective. And there's so much we can do. Keeping in mind, let's just look at on my perspective, let's keep that worst case scenario, the high emission scenario, on the table and look at it, because it is in some ways a proxy for the extreme events that we can't model yet, right? There is very little that we can get yet. We don't know how bad a Fiona hurricane can be 10 years, 15, 20 years down the road in a high emission scenario. We have suspicions, but we don't know. We don't know how bad a really bad heat wave in Atlantic Canada will be, right? We've seen BC, that was pretty scary, over 500-600 people that died. So I think the story isn't around, oh, you know, maybe we're doing better than the high emission scenario. The story is that, well, how can we actually function and act right now and be in a better position 10, 15, 30, 50 years down the road than we are right now to deal with those. And not from a disaster mitigation or disaster management, but really from community resiliency point of view.
I think that's a helpful perspective, right? The high-end scenarios get us ready for, if you're recommending that people take a look at something like Fiona and recognize that that's part of the current climate, if we're not ready for it, we should probably get ready. Then the high-end scenarios give us a sense of what other surprises we might be facing. There's a question here in the chat referencing the fact that, yeah, there seem to be surprises. There's a discussion or a reference here to what appears to be a slowdown of the Atlantic meridional overturning circulation, which, you know, I think is tied to some of these alarmingly high sea surface temperatures that we're seeing in the Atlantic Ocean right now. Is this something that these scenarios can help us with, or is this an outside conversation that we need to have as we recognize these perhaps climate surprises? I wonder, maybe Dr. Schweizer, how did these climate surprises maybe factor into some of those scenario designs, or are they just outside of that particular consideration?
Well, this is something that I also invite Christian to comment on, because that where I've been involved in the scenarios has been in sort of specifying the different socioeconomic drivers behind the emissions. And so typically, we kind of hand things off to the climate modeling community, and then that's where they like really figure out things like impacts on the AMOC and whatnot. But I imagine, again, I like how Dr. Dietz brought up proxies. So even if what the integrated assessment modeling community is able to produce is, here are the reasons why you might end up with high scenarios. So SSP5 describes a future that is actually prosperous in many ways. And also the demographic transition is successful in many countries. More women are in the workforce, all kinds of very nice things are happening in SSP5. But the way that we get there is by continuing to use fossil fuels for as long as we can. And so that is part of why the emissions look really crazy in SSP5. But then there are other socioeconomic conditions, such as SSP3, where that describes a breakdown in geopolitical cooperation. So that has bad implications for the UN Framework Convention on Climate Change. This is why we don't meet mitigation goals. And then you also end up with a high emissions trajectory in SSP3. You also have, breakdown in international development, huge global population. You've got like over 12 billion people. And so those are other things that can lead to an outcome of having high emissions. And so this is where I think that Dr. Seiler would be in a better position to comment on whether or not, with like SSP3 and SSP5 scenarios, if that's sort of the way that we start to understand these really extreme impacts that we hope don't manifest, but are tipping points that we need to watch out for.
Christian.
Yeah, so thank you, and thank you for bringing this up also here in the chat room. So all CMIP 6 models, so the CMIP 6 models are the ones that contributed to the last assessment report, the 6th assessment report from the Intergovernmental Panel on Climate Change, and they all look at the weakening of the AMOC, and all of them project a weakening of the AMOC. They all have it in there. But in those simulations under SSP5, there is no breakdown of the AMOC yet. But there has been a paper published last month that shows that, yes, the community Earth system model by NCAR, the National Center for Atmospheric Research in Boulder, Colorado, in the United States, that model is actually able to reproduce or to project collapse of the AMOC. So it's, again, something that's physically possible, but the majority of the models don't project that yet. It's very important to bring out, and there are two things here. One is extreme events and one is tipping points. The reason why we need to be cautious about, so one of the things that Sabine said very nicely, it's useful to look at the high-end scenarios if you think of extreme events, because in many instances, those extreme events are not are underrepresented. And I just want to explain why this happens. Earth system models are insanely computationally expensive. In order to make it feasible, they run at a relatively coarse grid. So the spatial grid is like 100 times 100 kilometers, in most of the cases close to the equator. And so a lot of the processes that manifest themselves as extreme events are not, cannot easily be simulated at such a coarse resolution. So very intense extratropical cyclones, such as explosive cyclones, etc., are underrepresented in the current generation of climate models, likely due to this coarse resolution. So if you want to look at the impact of climate change on extreme events, you can expect that even if you look at a high or a fossil fuel intensive scenarios, the change in extreme events is possibly underrepresented or underestimated because it's difficult to represent those extreme events at that coarse scale. Now with tipping points, that is a huge area of research that I'm also dedicated into, where a lot of the processes are not included. So for instance, if we think of wildfires, many of the Earth system models that contributed to CMIP6 don't even have wildfires, for instance, right? And they're still in development. So they're not even able to reproduce that tipping point because it's just not part of the process yet. So a lot of the surprises can still happen in the next IPCC assessment report as those processes are being included.
So I wonder, Joe, hearing about all of these surprises and extremes that the models that ultimately give us our projections don't handle very well, I wonder what does that trigger for you as an engineer when you're thinking about quantifying the uncertain and being ready for worst case scenarios when you're told, well, a bunch of really concerning things can't be managed in the data that we have right now, or the projections we have right now?
Yeah, well, one of the things is that in a lot of cases, infrastructure design, the guidelines and the regulations, for some of the smaller return periods, like a 30-year, 50-year, these are changing, of course, but that's not a worst case, right? I mean, in the sense that the way I should put it is a lot of the infrastructure design, not necessarily critical infrastructure, but the high end, where you're designing from, these are shorter lifespans. It doesn't matter so much which scenario you use, because they're very, very similar up the next 30, 40 years. The same and similar amounts of change. It's the longer term stuff where that becomes much more important. And I believe that a lot of those, engineers don't tend to design for those levels, really kind of catastrophic levels anyway, because it's just too expensive. It's just not possible to do that. It's not straightforward, right? It really depends on what you're doing, how, what region you're in, what kind of changes you're expecting, but you always need. I mean, as an engineer, you always want to over design if you can, especially if there's property and life in danger, or at risk at some. You want to over design, so you want to know what the potential is, for the worst case, even though you might not design for it. You want to know. Personally, I believe that especially from a stormwater perspective, since that's my primary area, that we should be looking at potentially catastrophic events, because something like happened in BC a few years ago, that was multiple factor. That wasn't one thing. Those are invisible to the design process. They're not even, and whether the climate scenarios can capture that, and especially when they're extremes, is questionable. But we still need to know what a kind of an upper bound, so that it will limit our how far, what's the worst possible thing that could happen. We can't, it might be low probability, perhaps if it's in the interest to have maybe plans for that, not necessarily infrastructure design, but this is where you get community action, and as Sabine was talking about, the engineering aspects of this are a small part, and quite frankly, they're simple. They're the simple parts. It's all the rest that's much more difficult. But again, yeah, from the engineering perspective, I want to know how bad can it get, and then kind of pare down from there. And I think that's kind of the best way to approach this. Because one, you do have at least a notion of where you can't pass this level of protection because it's just too expensive, and so I think that would help you kind of look for alternatives to simple hard engineering solutions, where you can use some mixed solutions, nature-based solutions, but also get communities involved, and resilience plans, and let them know that an event like this is possible, maybe unlikely, but possible. So if we reach that threshold, you got to trigger other things besides just the infrastructure. I don't know if that answers the question, but it's yeah. I'll stop there.
Yeah, no, I think that's useful. You're talking about the difficulty of quantifying very low probability events, but also balancing that with considering what options are feasible. Always a difficult calculus, particularly when the future is uncertainly constrained. There's a couple of other questions in here. I think one of them's already been answered in the chat by Dr. Schweizer about how different scenarios reflect some of the increasing conflict we've seen. The suggestion here is that the one that perhaps fits this is SSP3. So if you want to dig into some of those scenarios later on, maybe that's a place to start if you want to see the kinds of things that are happening geopolitically at the moment reflected in your scenarios. There's also another question down here about artificial intelligence and whether it's being utilized to advance climate modeling and scenarios. And Christian, it looks like you want to speak to this a little bit.
Yeah, so there are two things to keep in mind. One is the role of AI that plays for weather forecasts, and the other one for making climate projections. For weather forecasts, now we have artificial intelligence-based models that are competitive with the physics-based models. And the wonderful thing about these AI-based models is they take nearly no computational resources in order to run. So it's very expensive to train those models, but once they're trained, you can run them on your cell phone, basically, right? So that really may become a revolution in the area of weather forecast. One big disadvantage of those models is that they are intransparent. Nobody can physically interpret what is happening based on your model. The wonderful thing about climate models is that they're based on natural laws, and you can explain an outcome of the model based on those laws. So basically, a model is a way how we formalize our understanding of how the climate system works. The use of AI and climate modeling is a little bit different. So one of the things that I do in my research program is I try to integrate climate modeling and global Earth observations using artificial intelligence. So the models, they have many different parameters. Those parameters, they determine the outcome of the model, but it's very difficult to find the right parameter value because they're difficult to constrain from observations. Now, you can use a machine learning algorithm that basically marries your numerical simulation and your global Earth observation in a way that it finds the right parameter in order for your model output to be consistent with global satellite data, for instance, right? And so that's a way how we can produce more reliable models that then hopefully also result into reliable projections. Another way how AI is being used in the climate modeling community is to replace parameterizations. So we already talked about one of the disadvantages of those models is that they have a very coarse scale. Many of the processes cannot be physically represented. You cannot simulate every raindrop in there, so they need to be what's called parameterized. And many times those parameterizations are based on statistics of a statistical relationship between two variables, right? And so those kind of submodules could be replaced by artificial intelligence models that really feed on all the global Earth observations that we have. So these are the two main streams of use of AI and climate modeling. And the overall idea is that it will help to build more robust models with more reliable projections.
Excellent. So we've got about 10 minutes left in our scheduled time slot. I think maybe what I'll do is come back to the problem that Sabine has laid out, that we are trying to deal with a mess of information. And I wonder if any of you have suggestions for how we might be able to unmuddle, to dig out from that muddle, to help practitioners find a way out of some of the confusion of the data that they have available to you. Do you, based on this discussion and prior thinking, maybe have some ideas for how we might get out of some of this mess? Anybody want to take that first, or should I just start calling names? Sure, Sabine.
I think we got to realize that it takes a lot of work to walk people, and people, I'm just throwing this as a big kind of people, to walk everybody through what we mean by the climate is changing, what are the impacts, what are the risks that you're facing. And these are at this stage not things that you can meet with, let's say, an infographic or a webinar. These are conversations that you need to have, right? Because I always go back to COVID because in the end, it's a risk question, a risk tolerance question. So I always go back to COVID and say, you remember when, you know, everybody was asked to stay home and yet people still didn't stay home. People went out, people partied, and they wore masks or didn't wear masks. You know, everybody made a personal decision about their level of risk tolerance. And so when you think about climate, we all will make risk tolerance decisions. I live in a house that's in a floodplain. I have looked at the maps, the fantastic New Brunswick maps, which give depths of water in 2100. all of those terms, right? They're all still, we all still need to interpret them. But I know if there is a serious breach of the Chignecto Isthmus, a critical infrastructure that is currently not protected from any extreme events, if there is a breach, it could reach our house. My basement could be flooded. Now, I'm not going to run away screaming and say I can't stand the risk that I'm facing. No, I'm saying, okay, I understand that. I don't think it's going to happen, but I have no clue, right? I have no clue if Fiona's going to come up the bay tomorrow. Well, not tomorrow, but at some point, I have no clue. But I decide that, no, I'm comfortable with taking this risk. And so we all do, and politicians do. And everybody, every municipality needs to be able to make a conscious decision about risk. And I think that's where Dr. Daraio mentioned as well. You can't really build to the absolute worst case scenario. You can imagine all sorts of really bad scenarios, but you can't build to that. I mean, the world can't afford it. So there's always a measure of making a decision. We can take this, but we can't take that. So, but that means you have to have conversations. And at this stage, it is not so much of how many maps, how many infographics, how many communications materials we throw at people. It is way more these conversations that we have on the ground with groups of people, with communities, with decision makers, just trying to move them away from this is a one-off thing to, hey, we continuously will need to make those decisions on risk tolerance and how we look at the future, whether you have a 4-year time frame for your political career, or you have, you want to be a CEO of a municipality for the next 25 or 30 years. And I think we missed the point in thinking that, we don't need these people on the ground that are literally the intermediaries of interpreting all of what is coming at us as people, and all of that which needs to be incorporated into making decision. And I don't think we're at a stage yet where we can really have these good conversations, where we can say confidently, all right, so now the group that I just talked to, I am confident they understand what risk they are facing. They understand what potentially could happen. They understand what their options are, and they will make future decisions based on all of those elements, which is really the purpose of adaptation, right? And so I think the idea that we can do things without a lot of intense conversations and mentoring and on the ground work, that's not going to work. It's just not going to work. But we've assumed that for a long time. We've assumed that we can just throw things out, see what floats, and then the wrong things float, right? The wrong things pop up, and we deal with the wrong things. Anyway.
No, that's perfect. Relationships for risk discussions. I like it. It's certainly a way forward. Joe, go ahead.
Yeah. I just kind of want to go back to one of the points Sabine made was about risk tolerance. And something that we kind of mentioned a few times and not really focused on is uncertainty. And if really one about the scenario choice, one from my perspective, and I said this, but I don't think I said it explicitly. If you don't know what can happen, how can you decide how much you're willing to take that risk? Or how can you make any decisions if you don't have a range of possibilities? I mean, we do it all the time, of course, but it's there. It's information that's there, and it's useful and it's important. And there's really, I think that it's like, why not use it? Well, of course, depending on the context, but that's the more knowledge and the more information you have, the better decisions you can make. And that in and of itself is enough, I think. And also, again, you can't say I'm willing to, you're willing or not willing to tolerate certain risk if you don't know what it is, in the worst case. So, nothing new, but I'm just saying it a different way.
No, that's perfect. Dr. Schweizer or Dr. Seiler, anything you'd like to add in terms of strategies for unmuddling? Sure,
yeah,
Vanessa.
so something that I would like to add, and I'm really on the same wavelength as the other panelists who have spoken so far, that when as someone who's like, an academic, I'm interested in scenarios for primarily academic questions is what I've been looking at. But nevertheless, the whole process of like doing decision analysis and trying to actually make decisions. something that I see sort of in the history of how a lot of work around decision science, right, came out like during the 50s with like the rise of computing and this hope, right, that if you could clearly specify what your objectives are, you've got good data, right, like there was probably this vision decades ago that if you just had enough information and you put together some good models, you can figure out what the best choice is going to be. But I think that we're definitely in a time right now where we can't necessarily adopt that old paradigm of like, if you just get the right data, you can like put it through a model, you've got you know, an optimization that's set, you can follow the decision and you can forget about it, right? We're definitely not in a set and forget kind of state right now. There's a lot that's uncertain. There's a lot that's changing. And also how Dr. Seiler brought up like the carbon budget, right? Part of why there's this like deep scenario uncertainty about is SSP5 still a relevant scenario with these like really high emissions trajectories? It largely depends on whether or not you know, the largest emitters really get their act together. You know, is it true that in order for us to get our act together, we need higher carbon prices? You know, right now that seems to be like the main policy tool, right, that we talk about. And the longer we take to try to, if we do decide that carbon pricing is like the way to go to actually like, you know, succeed at the long game of mitigation, if we achieve net zero in like 2080 versus achieving it in 2050, you have very different climate outcomes from those different kinds of lag times. And so this is where, going back to how Dr. Dietz said, we need to be having these like regular, deeper conversations about what are we trying to adapt to? What does it mean to be a more resilient community? And then in turn, what are the implications for, you know, our commitments to doing things like, I recently had to replace my heating system in my house. And by virtue of, you know, what I work on, I knew that I needed to upgrade to like a heat pump. And even though I also could see it was much more expensive to do so, I personally felt that that was an important choice for me to make. So I completely agree. Continued conversations. Hopefully the fact that we have these different scenarios, it kind of forces people to talk about these uncertainties. And then, yeah, talk about risks and talk about perhaps being willing to take the more expensive option because you're actually trying to do something that in the long run, you know, preserves property, preserves lives, and so forth.
Excellent. A response to what scenario should I use is, hey, let's have a conversation about risk. Let's have a, yeah, so perfect. Dr. Seiler, anything you want to add to this?
Yeah, I think there are 2 points that I want to raise that I think they haven't been raised yet. One is they're both related to the time scale. So if you look at short time scale, the difference between the scenarios is very small. And the reason why that is because the climate change impact that we're experiencing over the next 10, 20 years, that is driven by the CO2 that's already in the atmosphere. And that has to do with the fact that CO2 has a very long lifetime in the atmosphere. So by just adding a little bit, although it's a lot, but by just adding it, it doesn't have a big impact on the change in temperature. They start to divide, of course, as you move forward in time. And so when you're by 2100, of course, there is a large difference between these scenarios. Now, so if you're looking at very short timescales, the difference isn't so large. Now, let's say you do an infrastructure project and you think about a seawall where you think about, well, this is an infrastructure project that should last more than 100 years, right? So by now you already have to look beyond 2100. And one of the things that I think some people think is that at 2100, since the graph stops there, the temperature changes or is the same, right? It stays constant. But if you see SSP 8.5, it means there's a radiative forcing of 8.5 watts per square meter at the top of the atmosphere. And that means that the planet will continue to warm until the radiative forcing is 0. So after 2100, it will continue, the temperature, global mean surface temperature continues to increase. And the same applies to the low end emission scenarios. As long as you have a radiative forcing, you have a warming, and that warming continues after 2100. So thinking beyond that 2100 date, I think is also important, of course, in the context of your project.
Excellent. So we are just a couple of minutes over time. So I'm going to quickly thank again our panelists. What I've heard today is incredibly useful. Take a look at multiple scenarios. Don't discount the high end. Have a lot of conversations with people. And depending on your particular needs, maybe be sure that we're thinking about adaptation and climate action not as a set and forget approach, but something that has to be continually adjusted as our reality continues to shift and as perhaps some of these uncertainty envelopes expand or contract as more information shows up. We will again be posting this recording very soon, and I would not be surprised if we carry on these discussions at a later date. I think there's a lot more to unpack with this kind of thinking as people are grappling with how to actually approach adaptation. So again, thank you, everybody. Thank you, Dr. Vanessa Schweizer, Dr. Joe Daraio, Dr. Christian Seiler, and Dr. Sabine Dietz. I look forward to speaking to all of you again in the near future. Thanks.
Thank you.
Thank you, everybody.